So now when we understand coherence and memory models, we need a third primitive, which is called synchronization, in order to write really meaningful shared memory applications. First, we're going to look at an example where synchronization is not used. We're going to look at an execution where we spawn off 4 threads. They will all have read and write access to the shared variable sum that the parent thread initiated. So first they will make a test to see if sum is smaller than some constant n, and then if that's not the case, they will increment the value of sum by 1. And the code that's been going to be executed inside each one of these loops sort of looks like the pseudo assembler here. Sometime in the beginning we load some constant of the constant n into some register. Then we load the value of sum from that shared memory location out there in memory, or from our local cache if we're lucky, into register 2. We figure out if it's time for us to do a jump. If not, we make sure we get a fresh copy of sum from memory so we don't get a stale old copy. We increment it by 1 and we store the result out to memory again, and we keep doing this over and over again. So the question here is, what value will get printed here after these 4 threads have fallen out of the loop? So the correct value is any value between n and n plus 3. So as you see here, this assumes that Murphy has been evolved and we really managed to nail, in order for us to get n plus 3, that means the Murphy has been involved, and have to make sure, for example, that when sum is equal to n minus 1, which is the last time we will get into this loop, all these loops will enter about at the same time. So they will all load sum is equal to n minus 1 up here. They will all make the test and conclude that they have to go into the body of this loop. They will all start to load the new and fresh value of sum. However, maybe one of them is slightly ahead of the others and have already updated sum to now, instead of holding n minus 1, holding the value n. Okay, the one following it will load the new fresh value n from memory, and it will quickly change the value of that to n plus 1, and the one following it may see the new value, and so on. So it is actually theoretically possible that the value n plus 3 will get printed out here. So here's another question: how many additions will be performed when we together by all these 4 threads? And the correct value is any number between n and n times 4. And once more, for that to hold, Murphy has to be involved. So let's say that all of them, when n is equal to 0, all of them start, all of them will load n is equal to 0, all of them will conclude that they have to get down to the body of the loop. Once more, they will all load the value sum is equal to 0 here, and they will all add 1 to sum and try to store the value back. That means that all 4 of them now will try to store sum is equal to 1 to memory, and then if they keep working in sort of lockstep with each other like that, that means that when you come to the end of all these 4 loops, we have actually performed this addition 4 times n, even though the maximum value that's going to get printed, as we said before, is going to be n plus 3. So this is just a little toy example, of course, and what can go wrong when you write a parallel program. But if something can go wrong, it also will go wrong when you have computation with millions and millions of cycles. So we have to find a way to really be able to, for example, write this kind of statement, sum equals sum plus 1, in such a way that we know that it will get incremented 1 and only 1 time each time we do a summation. We do this by introducing what's called critical regions. So critical regions is a piece of code that's guarded by synchronization primitives. So here we have created a loop body that looks very similar to the previous example. We have put it inside two synchronization primitives, a lock primitive and unlock primitive. And this kind of writing code like this ensures that only one thread at a time can be inside this critical region here. So they will all try to get to the lock, but we're going to make an implementation of this lock primitive such we only allow one thread to succeed and get in here, and not until that thread performs the unlock operation can one other thread get in here and make its update. So this could be one way to use the critical section. Another way to use the critical section will be just to have it around the summation itself, as you see in this example. And of course, that really depends on what you want your program to perform. So when you implement your synchronization, there are three different components that the synchronization has to consist of. It has to have an acquiring method, which means that we can guarantee that exactly one thread can be in the critical region at the same time, or as we say, acquire the critical region. It has to have some kind of waiting algorithm, which means that if a thread cannot get into the critical region, it has to be a way for it to stand there and wait for its turn to get into the critical region. And we have to have a release method for the thread that's been in the critical region and now has to somehow signal to the other threads that it's out of the critical region, and which will make it okay for the next thread to get into that region. So first we're going to look at different ways of acquire a lock or acquire this critical region. So these days, so we've looked at sort of similar algorithms before. So the Decker's algorithm is sort of a kind of mutual exclusion way of ensuring that at most one thread can be in the critical region, but it's not a very practical or efficient way to achieve this. So instead, modern CPUs often have what's called atomic instructions that allow you to implement these acquiring methods much more efficiently. And one of the more simpler atomic method is an instruction called Test&Set, or TAS for short. So this TAS instruction specifies here one register and one memory location. And the semantics of the Test&Set instruction is that it loads the value of the data value of the memory location identified by this address out here. It loads that into the register 1, and atomically, without chance for any other instruction or any other thread to sneak in and look at what's going on, atomically it will write a constant back to that memory location. So for example, it can write a constant 1 atomically into that memory location. So once more, you read the old value of that location into R1, and then you store a new constant into that location, predefined constant. And in an atomic way, no other thread can sneak in and sort of get you with your pants down and when you're sort of half done with this operation. So this happens as one atomic action. Of course, there could be other constants than one used. So at Sun, we used the constant FF, so we wrote all ones into a byte location when we implemented a similar kind of primitive. So when one of these atomic operations is performed by the memory system, it looks like just an ordinary store or a write operation to the coherence protocol. So what happens here, in order for us to implement this atomic change to memory, is in two steps. First, the coherence protocol will get a writable exclusive copy of the cache line into the first level cache. So in the MOSI protocol, it's state M that we want our cache line in. So, and once that cache line is in state M, then the cache itself can do the atomic update on that cache copy. So now the CPU have to make sure that there is a way to swap the constant into that location that now sits in L1 and to get the old data value from L1 back to the CPU. But for the coherence protocol, it looks like just a store operation. So there are no new transactions, coherence transactions, snooping transactions, bus transactions that you need to implement for the implementation of any of these atomic instructions we're going to discuss about here. There are other examples of more complex atomic primitives as well. One is a swap primitive. So swap specifies one register and one memory location, and it simply is a more generalized implementation of the test and set. So swap takes the data that's stored in the memory location, puts it in R1, and at the same time takes the data that resides in R1 and put at that memory location. And once more, this is done at the L1, inside the L1 cache, given that we have a write permission. We have an exclusive copy of the cache line with write permission. It's even more complicated instruction is what's called compare and swap, or CAS for short. Here we define two registers, R1, R2, and a memory location. And so what compare and swap will do is we perform the swap operation between memory location and R1, as well as R1 to memory location in one atomic operation, only if the memory location's value right now is the same as the value stored in register 2. So, for example, only swap the memory location and the contents of R1. Only make that swap if memory location is equal to 0. So in that case, we had made sure that register 2 contains a 0 before we do the compare and swap operation. There are lots of other primitives as well, but typically you have with these three primitives you can do quite a lot of you can get quite far towards where you need to be when you write these shared memory programs. So now we're going to discuss the different kind of ways of weighting as well. So the acquiring is done with the atomic operation. The weighting is either done as a blocking weight. So this is, for example, in conjunction with the operating system. So if you, let's say you would like to get an exclusive access to a printer that's connected to the network or something like that, and let's say you can't get a hold of that printer, then you block, which means the process will go to sleep, and then the operating system will wake it up either when the printer is available or wake it up after some time so it can go back and see if that printer is available. So this is typically an algorithm you use if you're waiting for something that is expected to take a long time before it frees up. Busy waiting is used if you the primitive the critical section waiting for is supposed to free up fairly soon in nanoseconds or maybe up to microseconds, probably not milliseconds. That means that you're actively going to wait for that critical section to become available by testing some location in memory, for example, over and over again. It has much low overhead, but the drawback compared with the blocking algorithm, you will consume CPU power just waiting for that critical section to get ready, to get freed up. So you will not really make any good progress in the execution. You will burn energy, and maybe this CPU could be used to do some other good stuff. You can also, as we'll see in a little while, create quite a lot of coherence traffic with these kind of busy waiting algorithms if you don't design them with care. Also, of course, you can have hybrid methods. So you busy wait for a while, then you get fed up and you block, and so you don't use the heavy hammer unless you really think it's needed. And finally, the release algorithm. Typically, if it's a busy wait algorithm, you simply store some kind of constant to a memory location. You don't need an atomic operation here because there's only one thread that can be in the critical section at a time. So we know that it's only this very thread that's going to make this change, that's going to do the release of this lock. So just an ordinary write will do just fine. We're going to look at a couple of examples how we can implement these kind of acquire and release or lock and unlock kind of primitives. And we start with a primitive, fully functional example, but it may not be the most optimal example. So we're going to use that atomic primitive test and set. And we're going to use the test and set to inside one loop, and we're going to keep trying to see if that lock we're waiting for is busy. So the lock variable identifies the critical section that we like to get into, and the semantics is that if the lock variable it contains a 0, that means it's free. If it contains a 1, that means that somebody else is in the critical section. So here, this test and set of lock variables, I assume that this is some kind of macro that can be expanded to the necessary assembly instruction you need. So we assume that this returns the current value at the memory location. So this will return the old value at the memory location, and of course atomically write a 1 into that location. So here's the question. How is this task here inside this loop treated by the cache coherence protocol? Is it like a CPU read operation, CPU write operation? Or is it performed? Is there some kind of swapping performed inside the DRAM? So it is like a write operation, as we said just a couple of slides ago. So this is how you would implement the unlock. So unlock is the function you call when you get out of the critical region, and as we said before, it's a very common way is just to write some kind of constant. So here we write the 0 into that region, into that variable once we get out of the critical region. So this is a fully functional way of implementing a lock and unlock. Only one thread at a time can be inside between these two calls to the lock and unlock, and all of the rest of them will have to queue up and spin there in this while loop and wait until they see that the lock variable gets the value 0. The first one that sees that the lock variable has the value of 0, its test and set will return a 0, so it will fall out of this infinite loop here, and it will get into the critical region, and once it gets out of the critical region, it will set the lock variable to 0 to allow for the next lucky thread to get in again. So if two threads are waiting for the lock implemented like this, what will happen? They will both spin locally in their cache, they will create coherence traffic by invalidating each other, or they will both block and need to be woken up by the operating system. So unfortunately, the correct answer is the second one. They will both create coherence traffic because they will both be inside this loop. And each time they run in this loop, they will do an atomic operation to a specific memory location, and that will look like a write operation to the coherence protocol. So that means that each one of them will perform a write, and each time they perform a write, they have to invalidate the other one. So there will be a lot of ping-ponging back and forth by this cache line. So invalidating, or more specifically in the, if it's a Snoopy case, cache coherence protocol, they will have the read to write primitive. So they will need to read with intention to modify all the time back and forth. And that will unfortunately slow down the thread that is in the critical region, because they create lots of traffic, and our hero that's in the critical region, that's a thread we want to make progress as soon as possible. We want to get out of there so the other ones can get in. That is the thread that will be slowed down by this operation. So we need something which is slightly more intelligent and make use of what we now understand from how cache coherence protocols are implemented. So such a lock could be what's called an optimistic test and set lock, or a spin lock. So here what you have is a lock where it sort of looks like the previous one. We have an infinite loop here, while true, do all these things down to here. That's the lock. Okay. And the first thing we do in this lock in this infinite loop is we test once if the test and set will return 0. If so, we get out of that loop. So we execute the break statement here, which will get us out of the infinite loop. If not, we get into a different infinite loop here, which says while the lock variable is not equal to 0, just stand here. Okay, and then once we see that the lock variable is equal to 0, we're going to fall out of this loop and we get back to the beginning of this loop again. We're going to perform test and set once. If we're lucky and it returns 0, we declare success and fall out into the critical region. Otherwise, we're going to go down and spin here again. And the unlock is exactly the same as in the previous example. So here's a question about this lock primitive. If two threads are waiting for the lock, will they most likely spin locally in their cache? Will they create coherence traffic all the time by invalidating each other? Or will they both block and need to be woken up by the operating system? Unfortunately, the answer is the first one. They will mostly spin locally in their cache because they will do this test and set once, this operation that looks like a store operation. Then, if that didn't work out, instead of being stubborn and trying it over and over again, they will go into this loop, the while loop down here. And this while loop is just the normal test. It's not the test and set. So this will be a loop that contains a single load of the lock variable and then testing that with a constant of 0. So this is just a read load operation. And load operations you can do locally in your cache. So both threads will get a readable copy in the cache and it will happily spin at full speed very quickly in the local cache until the thread in the critical section decide to leave the critical section, change the value of the lock variable to 0. And if we have the MOSI protocol we discussed before, that means that the two spinning copies in the waiting threads caches will get invalidated first, and and at that point in time the lock variable only reside in the cache of the thread that just came out of the critical region, and after that the first of the two spinning threads that managed to perform the test and set operation will declare success and will fall out of this loop and will be in the critical region. So this algorithm creates much less traffic than the ponding operation. Still, there is some traffic at handover, lock handover, and we're going to discuss more options here when we talk about scalable synchronization algorithms. Here is a different version of this lock. This is, instead of the previous one, which was the optimistic test and set, this is the pessimistic test and set. So what you do here is that you assume that this critical section most often is occupied. So instead of starting your try to get the lock with a test and set, you start with a spinning. And only the first time you fall out of the spinning will you perform the test and set. So you're a little less aggressive. It takes a little longer for you to acquire the lock if the lock is free, but if the lock is busy, you avoid creating lots of some coherence traffic because you avoid the first test and set. But that's really the only difference between those two algorithms. Lastly, let me show you what I meant with that these kind of locks, both the optimistic and pessimistic lock, can create lots of traffic right when you release a lock. So let's assume here that we have some number of threads all spinning in the local caches. So that's its circles here. And we have one happy thread which is in the critical section. That's a CS thread. We also have the lock variable out in memory. So the lock variable has the value 1 since some thread is in the critical region. Right now there is no traffic generated on this interconnect because all of the spinning threads have a readable copy in their cache. Now comes the time when the thread in the critical region, critical section, wants to release the lock. So it's going to try to write the value 0 to the lock location. So globally now this is the value of 0, even though that value only right now resides in the local cache. But we also know in order for it to get write permission, it invalidated all the other caches. So they no longer have a cache, but they are still as eager to keep spinning in that little while loop. Next thing that happens is that that spinning activity will bring in a copy of the lock into all those eagerly spinning threads caches. So now, pretty much at the same time, they will all see that the lock has now changed value to 0. They will all of them declare success and saying, this is what I've been waiting for. They will fall out of this while loop where they did the nice test using a read operation, and then we'll all get aggressive and try to perform a test and set operation in the network. And as we know, test and set operation looks like a write operation. So that means that they will start to invalidate each other back and forth like crazy. One of them will be locking it in the first, but all the others will keep invalidating, doing all these tests and sets. And then if you sit down and think about this property of this kind of algorithms, you can actually get n squared over 2 reads performed in a situation like this if Murphy is involved and all these tests and sets and reads are interleaved in a really bad way. So you still create lots of traffic right when you hand over the critical section. And if you are handing over the critical section fairly often, that means that the total amount of traffic generated in the system can still be very hard. So the fix to this is to, as we will discuss later, is to use some kind of backoff strategy. But backoff strategy is not always good for the handover latency, time it takes between you release a lock and you require it again. Another fix we'll discuss are queue-based locks as well, but more about that later.